In this video, we are going to do some examples evaluating double integrals over rectangular regions. So the first problem says find the volume of the region bounded above by this equation and below by the region given by these inequalities in the xy plane, where our distance is given in centimeters. So this is going to involve setting up a double integral. So I want to first pause the video for about 3 minutes to have you try this first. So pause it in 3, 2, 1, pause it and try it. Okay, so hopefully did that. Hopefully paused it to try it. Let's talk about it. So I'll do this in 2 ways. So method 1. So let's set up our double integral. So I'll have my double integral of my function. Remember, to find the volume, I take the double integral of this function. So we got that e to the x over 3 y squared. I got to pick some order of integration. So maybe I'll do dx inside and then dy outside. It doesn't really make too much of a difference for this problem. And if dx is inside, the inner integral has to be in terms of x, which goes from 0 to 3 here. So x goes from 0 to 3. Normally I'd write, x equals and x equals. But as we get more practice with these, we typically tend not to do that to save time. And we just keep in mind that, okay, because these values go with the inner integral, and that has a dx, they're in terms of x. So the outer one is in terms of y, and those values go from 1 to 2 in this problem. Okay, so the first thing I'm going to notice is my function can be split into a product of a function of x and a function of y. And when I see that, and my region is a rectangle like it is here, we can do what's called decouple this double integral. So when I decouple it, I get to split it up and multiply 2 integrals together. So one of those integrals will be the dx integral, and one of them will be the dy. The dx one takes this x, the function that's in terms of x, e to the x over 3, and then I write those limits of integration, the 0 and the 3, because those are what go with the x. And then the function in terms of y was y squared. Let's write those limits, which are 1 to 2. Okay, so I'm ready to do some antiderivatives. So the antiderivative e to the stuff usually involves that e to the stuff, e to the x over 3. But I can check if this is right by taking its derivative and seeing if I get back this thing. So the derivative e to the stuff is e to the stuff times the derivative of the stuff, which would give me a 1/3. But I don't see an extra 1/3 here in front of this. So I'm going to need to cancel out this 1/3. And the way I cancel that out is I put a 3 in front. So I'm going to have to put a 3 in front here. Now when I do the derivative of this, I get back that function. Okay, and then plug in the 0 and the 3. I'll put a parentheses around this. For that y squared, the antiderivative is y to the 3 over 3. Okay, and then I'll have to plug in the 2 and the 1. Okay, close the parentheses. All right, for this first term, if I plug in 3, I'll get 3e. And then minus, if I plug in 0, I'll just get 3. And then for that second parentheses, plugging in 2, I get 8/3. Minus plugging in 1, I get 1/3. Okay, so I can factor a 3 out of the first parentheses. I'll get 3. Let's see. Well, okay, how do I want to simplify? Yeah, let's factor a 3 out. And then times e minus 1. The second parentheses becomes 7/3. I can cancel the 3's and I'll get 7 times e minus 1 for my volume. And the distance it said is in centimeters, so my volume should be in centimeters cubed. Okay, cool. So let's do this another way. I just want to show you that this can be done in more than one way. So method 2 is, let's do the integral, this double integral, by iterating it, doing one integral at a time. This is the first way we learned how to do these. So I'm going to take my double integral, so 1 to 2 on the outside, 0 to 3 on the inside. e to the x over 3 times y squared. And then I have dx inside, dy outside. And I could swap the order of these if I wanted to. I could make it work in either order. But let's just do it this way. So I do the inner integral first, which is the dx integral. And that means we got to treat x as a variable and treat y as a constant. Okay, so let's write the outer integral, 1 to 2. And I'm treating y as a constant, so this y squared will stay multiplying the antiderivative of e to the x over 3, which we just did. That's 3 e to the x over 3. And the y squared just stays multiplying it because it's like a constant. And now I'm going to plug in, this is x equals 0 and x equals 3. I'm choosing to write these x equals just because, so now when I plug in, I remember which variable to plug in for. And then I got my outer dy. So if I plug in, I'll get integral from 1 to 2. And if I plug in 3, we'll get 3e y squared. Minus, if you plug in 0, we'll just get 3y squared. And then dy. So notice that once we've done the dx integral and plugged in, all the x's should be gone. If they're not, we made some mistake. Okay, so now I'm ready to do these antiderivatives. E is like a constant, so that stays there. And I'll get e times y cubed, right? Because that's the antiderivative of 3y squared. And then minus, for that next term, I'll also get y cubed. Then I got to plug in the 1 and the 2. All right, so if I plug in 2, I'll get 8e minus 8. And then subtract what I get if you plug 1 in, which will be e minus 1. And if you combine like terms and distribute, we'll get 7e minus 7, which is the same as what we had here, centimeters cubed. So nice, we're getting the same thing. I'd encourage you to pause and check that if I swapped the order and did dy first, we would also get the same thing. Okay, so let's end the video with one more example. Let's say I want to evaluate this double integral here. So in the order in which it's written with the dy inside, for this we would be treating x as a constant. So we'd be treating x as a constant. So what would that antiderivative look like? So let's first just imagine x is a constant, like 3. So that inner integral would be from 0 to pi. We have y times cosine of, let's just plug in like 3 for x, 3y dy. So I want to have you briefly pause the video for like 30 seconds to see if you can remember what method do I use for this integral. So pause it in 3, 2, 1, pause it just to think about what method do I use. You don't have to evaluate it, but just think about what method. Okay, so hopefully you pause it to think about that. For this, we need integration by parts. Integration by parts. One of the tip-offs is we have two functions multiplying each other of like different types. This is like a polynomial, this is a trig. Often when you have two different types multiplying each other, we need parts. Okay, so I could do it that way, but it'd be nice if I can avoid by parts. So it's making me think maybe let's do it in the other order. Because if I do it with respect to dx first, there's only one x in here. So it's kind of like there's just one variable. The y's are like constants. That seems easier to do. So let's swap the order. We do that by Fubini's theorem. That's what lets us do it. So that is going to give me the integral from 0 to pi outside, 1 to 2 inside, our same function, y times cosine of xy, and then dx now inside, dy now outside. So when I look at this inner integral, it's dx, so x is like the variable, but y gets treated as a constant. So treat y as a constant. Okay, so doing this, I get the outer integral from 0 to pi. And now when I do this antiderivative, y gets treated as a constant. So this y in front just stays multiplying the antiderivative of that cosine term. So that y just stays there, multiplies. I know the antiderivative of cosine would give me a sine. So I know I'd have sine of xy. But then am I going to need to adjust it by a factor? Because the derivative of this requires chain rule. The derivative of sine gives me cosine, and I'll get cosine of xy. That multiplies the derivative of the inside, which if I'm treating x as the variable, the derivative of x becomes 1, and the y just stays there multiplying that. So this will pop out a y. And I need to somehow cancel out the y, because I don't see an x. I need to cancel out the y. And the way I do that is I need to put a 1 over y in front of this. Okay. And all right, then I got to plug in my limits of integration, which go from x equals 1 to x equals 2. I'm writing the x equals here just so it's clear that I'm plugging for x rather than y. And then the outer one's dy. But this is nice because the y's cancel. In fact, you might have even recognized from the get-go that if I look at this whole thing collectively, the antiderivative of that would have been sine of xy straight away, and that would have been a little quicker. Okay, but nonetheless, let's plug in. I'll get 0 to pi. If I plug in 2 for x, I'll get sine of 2y. Minus if I plug in 1, I get sine of y dy. Now I can do these antiderivatives. So this first term, let's see, I'll get minus 1/2 cosine of 2y. And then for the next term, I'll get plus cosine of y. And now I got to plug in the 0 and the pi. If we plug pi in, cosine of 2 pi is 1. So the first term is negative 1/2. Cosine of pi is minus 1. All right, and then minus, if you plug 0 in, I'll get minus 1/2. Cosine of 0 is just 1. And then plus this cosine of 0 is 1. Okay, and if you simplify this, this works out to minus 2. And that is our answer.